We're live.
All right, so it's great to be here. So hi, everyone. I'm Osbert Bastani. So I'm an assistant professor at University of Pennsylvania, working broadly on trustworthy machine learning. And today I'm going to be talking about some of the work that my group has been doing on large language models for code, mostly focusing on program optimization, but I'll also touch on some other aspects of LLMs for code. So just to kind of give the context, so I think over the last 5 to 10 years, it's been pretty clear that machine learning is going to kind of revolutionize the way that people write code and develop software. So there's already been a lot of impact on this kind of in programming languages where we've used machine learning for things like program synthesis, program verification, software testing, and so on. And this was really turbocharged a couple of years ago when LLMs kind of became mainstream and really when GitHub released their Copilot tool, which showed that LLMs can really write good code in a really useful way. And since then, of course, there's been a huge kind of boom in work on both products that leverage LLMs for various coding purposes, as well as kind of Copilot like tools in other contexts. And the kind of quality of these tools, I think, for someone who works on programming languages, has worked on programming languages for a while, it's pretty surprising how good these tools have become. When we were just starting, it was mostly symbolic systems that were you do like program synthesis and you do search with some machine learning to guide the search. But nowadays, fairly neural-based systems can do really, really well at programming. So just to kind of give two examples, I'm sure a lot of people here have heard of AlphaCode, which is a tool out of DeepMind designed to solve Codeforces problems. And they were able to get 45th percentile in the, so Codeforces is a coding competition, and they were able to get 45th percentile of performance among human competitors, which is quite impressive. So it's not expert level. In fact, it is quite far from expert level still, but it's like an advanced beginner kind of level. And of course, GPT-4 can do a lot of things, and one of them is write good code. Here I'm showing an example where I've asked it to write some React code to incorporate, to design a kind of a system where it can, or a web page where it can show a Python interpreter. And this is a really hard problem because, it has to reason about different libraries. It has to kind of build components in multiple places. But GPT-4 is able to do a surprisingly good job at this. So something that was unimaginable for program synthesis just 5 years ago can now be solved basically out of the box with the foundation model like GPT-4. And these gains aren't just, they aren't just parlor tricks. So there's a lot of evidence that these kinds of tools can actually improve programmer productivity. So this is a study out of GitHub using their Copilot tool. They showed that users who use the tool could actually develop a web server much more quickly than users who were kind of not given a tool and had to do it the old-fashioned way without AI. And in fact, the decrease, it went from 2 hours and 40 minutes all the way down to 1 hour and 11 minutes in their study. Just last week, just in a kind of another example, this isn't code completion, but this is actually LLMs for testing at Meta. So they showed that you can use LLMs to generate or improve unit tests and actually get 25% of the test cases they improved actually ended up getting better coverage compared to the original test case. So really, there's a lot of potential behind LLMs to improve a lot of different programming tasks. Beyond just improving programmer productivity, however, I think LLMs for code are also promising in another way. So there's also been a lot of interest in using program synthesis and symbolic methods to improve machine learning systems. So things like neurosymbolic learning, programmatic reinforcement learning, neurosymbolic generation, and so on. And this has also been turbocharged recently by LLMs. So here we're thinking about LLMs for code being applied to solve AI tasks. So this is a really nice example out of Google a few months ago where they showed this is a code as policy kind of idea where they take a natural language task specified by the user, they give it to a large language model such as GPT-4, and then GPT-4 will output a program in Python. And when you execute this program on a robot, it can solve the task that the user wanted. So this really shows that, we're not just talking about improving programmer performance, but even if your goal is to solve AI tasks, having these LLMs for code can be really, really helpful. So of course there are, this is all great, but there's still a number of challenges to actually getting these models to solve problems at scale. So one of the biggest challenges is that there's still this kind of ongoing debate about specialized versus foundation models. So some of the models I told you about are specialized, some of them are foundation models. AlphaCode is actually a fairly specialized model. So this is the one for code forces. And training AlphaCode is really, really expensive. So it took more than 2,000 petaflops days of compute and 175 megawatt hours of energy, which is about 16 times the average yearly household energy consumption in the US. So clearly, if every single new task we need to train a new model, that's not going to work. And the promise of foundation models is that, we can train GPT-4 once. Yeah, it might cost hundreds of millions of dollars, but once we have that model, we can use it for a lot of downstream tasks. Okay, so how well does that work? Well, I told you AlphaCode is in the 45th percentile of code forces problems. If we look at GPT-4, it actually only is in the 5th percentile. So that means 95% of human competitors actually outperform GPT-4. So just using foundation models out of the box clearly isn't enough, and something needs to be done to adapt these models to the tasks that we want to solve. So that's the first challenge. There's also kind of a challenge that I think we see it a lot more generally for language models, this problem of hallucinations. In the context of code, this just means that we're getting wrong code, right? So GPT-4 very happily gives us buggy code, code with security vulnerabilities, and so on. This is just one example I found on the web. So here, GPT-4 generated some code, and it's not doing proper input validation. So this is for a Flask application. Right. And so it can if you're a novice programmer and you don't really know best practices, you're getting this code that's actually not very good and can lead to poor code quality down the line. So today I'm going to be talking about a couple of directions to try and address some of these challenges. So I'm going to first talk about adapting code foundation models to program optimization. And I'm going to spend most of my time talking about that. And then I'll touch on a couple other directions. So first, a similar kind of idea, how do we adapt code models to reward design? So this is an instance of the neurosymbolic learning setting that I told you about a little while ago. And then also I'll spend some time talking about uncertainty quantification for code LLMs to try and address some of these trust issues. Okay, so first I'm going to talk about learning performance improving code edits for program optimization. So this is work that was led by my student Alex and Aman, who's a PhD student at CMU, and done in collaboration with Amir and a bunch of other people. So and Amir is at Google. So here we're looking at program optimization, which I think is a really nice example of a task that we might want to try to adapt LLMs to solving. So program optimization actually has a long history because in programming languages, because we all know that Moore's law has basically already come to an end. So if we're going to squeeze more performance out of the hardware, we can't really rely on the hardware itself getting better every 2 years. We actually have to write more performance software. So there's been a lot of interest in automatically speeding up code. And if we're thinking about the machine learning paradigm for doing so, I think it's pretty straightforward. So you want to give a neural network a slow program and have that neural network spit out a faster implementation of that same program. So the state of the art was, for a while, was based on kind of pre-deep learning techniques. So this is Stoke, a stochastic super optimization system, which basically uses MCMC algorithms to search through this really large space of assembly programs in order to find versions that are faster than the original input. And in this example here, Stoke can actually, you give it an assembly program and it actually have the number of instructions in that assembly program. But naturally, with LLMs, this is a really huge search space. So using LLMs to kind of guide the search is a really natural idea. So a few years ago, DeepMind released this tool, AlphaDev, to solve the same problem using similar techniques, but with a neural network in the loop. And they were using Monte Carlo tree search instead of vanilla MCMC. And we get these really cool results. So they took some very kind of fundamental sorting algorithms and showed that you can actually speed them up by improving the assembly instructions a little bit. But of course, this is going to suffer from this kind of, it's a very specialized system. And actually, it's even worse than, what you might imagine something like AlphaCoder. So AlphaDev is actually retrained from scratch for every optimization problem that you're trying to solve. They basically target a single optimization problem and run reinforcement learning for a really long time in order to solve that problem. And it can take a really long time for this to converge. So again, a natural question is whether we can use foundation models to solve this task. So it turns out that if you try to use I'll show some results along these lines in a moment, but if you try to use foundation models out of the box, it's not going to work very well. So you really do need to do some adaptation in order to get this to work. One natural strategy is to use reinforcement learning. So here the goal is to kind of optimize program performance, which is this real valued outcome. So you could imagine trying to use RL to solve this problem, but as with AlphaDev, that's going to be a really expensive strategy. And it's actually going to be much more efficient if we can reduce this to supervised learning. But then if we want to reduce it to supervised learning, we need good data sets in order to be able to do that. There's a second challenge, which I'm just going to touch on briefly, but that's that actually benchmarking programs can be really unreliable. If you think about, if you think about trying to run a program on your CPU and time how long it takes, that can vary a lot depending on the current workload and the kind of choices in the OS and the CPU. So CPUs are really complex objects. So depending on, what your memory is and everything, this can vary a lot. Just to kind of demonstrate this, we took a bunch of programs and we benchmarked them against themselves. And we found that a program was often faster than itself, right? Which is obviously a nonsensical result. In fact, in 5% of cases in this benchmark, we found that we had a speed up of almost 2x, which is kind of insane. I think in some of the examples I talked about earlier, they use the size of the code as a proxy for how fast it is. When you're doing assembly, I think that's okay. It's still not probably the most accurate thing, but as you're scaling up to kind of higher levels of abstraction, this is going to quickly become a really bad proxy. So to solve the first challenge, we introduced a data set that we call Pi. So Pi here stands for Performance Improving Code Edits. And basically the idea is Pi is based on the CodeNet data set, which is a competitive programming data set. So it has a bunch of user submissions for a lot of different competitive programming problems over time. And the really nice thing about CodeNet is it actually has multiple submissions for a single user over time for the same problem. So what you get to see is a user write a draft of a program, and then they realize, maybe there are some things that they can speed up, maybe they can make it faster in some ways, so they improve it, and then they do this over a series of steps, right? And we get all of these submissions in our data set. So a very natural thing to try is to look for slow, fast pairs in this data set. So we'll go find a slow program and a fast program written by the same user. And this we can think of as a supervised learning example of how to speed up the slow program to get the fast program. So that's exactly what we did. We looked at sequences of submissions made by the same user for the same problem. And if there was a subsequent submission that basically improved the performance by at least 1.1x, then we're going to include that as an element in our training set. So using this, now we have a training set that we can use for supervised learning to train language models for program optimization. So one thing to note here is there is a question when we're doing optimization about how we check for correctness. So verifying the program optimizations, that would be great, but it's a really hard thing to do. So we're going to focus on test cases to check correctness, which is kind of standard practice in the field. So basically, we actually used, so AlphaCode also had this problem, and they used LLM-generated test cases to augment the test cases that are already there in CodeNet. So on average, we have about 80 to 100 test cases per problem. Okay, so that's the data set we used to solve the first challenge. For the second one, we're going to be using the Gem5 system simulator. So this is the stochasticity problem. Basically, we're going to use a CPU simulator in order to solve this problem. So Gem5 is a kind of gold standard system simulator. So it simulates how fast a program executes on hardware, including the CPU, memory, I/O, and other things. And it gets pretty good. It's deterministic, so that's fantastic. And it gets really, really good kind of estimates of the performance of code. So this basically solves our challenge of how do we get good execution time measurements. So now with these two pieces, we can use them to benchmark a bunch of different ways for trying to adapt LLMs to solving the program optimization problem. So we tried a lot of different techniques. I'll go through all of the different techniques we tried in a moment. And we found that basically you have to be really careful how you design your techniques in order to get them to work well. So we've considered both black box techniques where we don't need any fine tuning, as well as kind of fine tuning techniques where we're actually going to train our model on the data set in order to try and improve performance. And to evaluate, we're going to consider a couple of different metrics. So our main evaluation metrics are the percent optimized. So that's the fraction of programs where we made it at least 10% faster while passing all the test cases, as well as the average speed up in running time. One note here is that we'll default to 1.0 speed up if the program is slower or if it fails a test, because in program optimization, you should never do worse than the initial program that you started with. So these are our main two metrics. I will also report the percent correct, which can sometimes be just to kind of how often is the model generating something that actually satisfies all the test cases. All right, so yeah, the first technique that we tried was kind of a very standard instruction prompting technique. So this is if you're, what most people who use GPT nowadays are just doing some kind of instruction prompting. And for a lot of tasks, it actually works pretty well. So here's the prompt that we did. We also tried a couple of different ones, but this is the one we finally used. It's a very simple thing. It just says, given the following program, try to improve its performance. And then we give it the source code, and then we ask it to optimize it. And here are the results. So we tried both open source models, so focusing on the Code Llama models, which at the time were the best open source code models. And we also tried some of the both GPT 3.5 and GPT 4. And as you can see, so we are getting a moderate speed up, especially with GPT 3.5 here. So we get 1.4x speed up. But this is actually not that impressive. So the reason is that in our data set, we're actually including all programmer submissions, right? Not just their fastest ones. So there's actually a lot of leeway for improvement. And we'll see that, the ceiling here is actually much, much higher. So 1.5x, it's good if you're starting from expert, really fast code, but it's actually not so good if you're just starting from a first draft of code or something that is still in progress. So that's the best we can do for instruct prompting. Next, we tried few shot prompting. So kind of a really natural, again, a very popular technique for adapting language models is to give it a couple of examples. So here we choose just a handful of examples. I think we choose 2 examples from the Pi data set, and we use those to prompt the model. So we just show the model the 2 examples, and then again, we give it the program, and we ask it to produce the optimized version of the program. And then we see how well that works. So here, it's actually a little worse, which was a little surprising, but it's really in the same ballpark. So we get about 1.44x improvement in performance through few shot prompting. So again, it's not really, these examples aren't really helping the model learn how to optimize programs. And we were a little surprised at first. We thought this would work better. But if you think about it, program optimization, it's not something the model necessarily knows how to do. And just giving it 2 examples, you're not going to magically learn how to optimize programs if you didn't already know how to. Yeah?
So let me just understand your previous slide a little bit better. So you asked it to iterate for capital N times. Then how is it possible that, so wouldn't it report the best out of the capital N?
No, these aren't iterations. Sorry, these are n examples. So here n equals in our experiments n equals 2, but we're giving it 2 examples.
But then can you prompt it to iterate on itself capital N times?
Yes, you can. We didn't actually try that. That is something that could help. We didn't have too much success with that, but yeah, yeah. Yeah, and there is evidence showing that, I mean, it's probably mixed. There is evidence showing that a lot of times when you just try to ask it to improve itself, you might actually be better off just taking more samples from the model. So that's something that's kind of still fuzzy, whether this feedback actually helps. I will actually, we did actually have more luck with feedback in a second project I'll talk about, which we'll get to. So yeah, that was few shot prompting. And the third kind of natural strategy we tried was chain of thought prompting, again, something that's really popular. So here we basically asked the GPT to first come up with a potential strategy for speeding up the program. And then we ask it to give an optimized version of the program that uses the same code as the strategy mentioned above. So this kind of splitting it into 2 pieces where we first ask it to think through the solution and then ask it for the solution. And kind of similar results. So this did improve performance a little bit. Now we're up to 1.6x speed up, but it's still not, it's still in the same ballpark. And really, again, I think the problem is that there's really no reason why we would expect these models to be able to speed up, to optimize programs given so little information, right? They don't really know anything about what it means for the code to run fast or slow. I mean, we don't know exactly what's gone into the training of these models, but there's not just like performance data on a lot of the code that's out there just lying around. We don't have slow, fast versions in typical training sets. So I think it makes a lot of sense that you can't just expect a couple of examples to speed up to teach these models how to do program optimization. And I think this is in line with literature showing that when your task is a little farther outside of what the model has been trained on, a lot of these kind of few shot and simple adaptation and in context learning strategies break down pretty quickly. Yeah, and the few in-context examples that we gave it probably weren't relevant to the current program that we're trying to optimize. So maybe a broader issue is, so we kind of swept it under the rug, but none of these approaches actually use the Pi data set in a meaningful way, right? So far, we haven't actually made use of the data set that we have. So a kind of natural strategy, if we want to make better use of our data set, maybe we should be looking for examples that are more relevant to the current program that we're trying to optimize. And in fact, there has been an approach like this studied in the literature. So this is called dynamic retrieval. And the idea is that when we're given a program, we're not just going to give it a fixed set of examples to do optimization. Instead, we're actually going to search through our data set to find examples that are relevant to the current program. So the idea is that we're going to take this program, we're going to feed it to CodeBERT, and then we're going to get an embedding, and we're going to use that embedding to do retrieval from the Pi data set, and we're going to retrieve these slow fast pairs. So basically, we're going to look for a slow program in our data set that looks like the program to be optimized, and then we're going to take the slow fast pair, that program and the corresponding fast program, and we're going to use those as in-context examples. So then it's going to look a lot like the in-context learning strategy or the few-shot learning strategy. We're going to give it, again, 2 examples retrieved from the Pi data set, and we're going to use those 2 examples to try to get a speed up. Okay. Yeah?
Program, is it made by like variable names and things like that, or is it really that I just don't know?
Yeah, so we didn't really do any analysis of that, but in general, I think the answer is yes, variable names are really important. I would guess if you obfuscate the variable names, it's not going to know what your program is doing. And I think that makes sense, right? Like if you showed this to a human and you obfuscate the variable names, they're not going to know what it's doing either. So there is a trade-off there where you want some robustness, but it certainly makes sense that having the right variable names is important. Any other questions? Yeah.
So I have a question actually on the prior steps with the few shot. Like, did you experiment with, let's say, increasing number of samples and seeing if that improved performance? Just trying to leverage like this notion of
Yeah, I think we played around with it a little bit. Not that systematically, but generally none of these techniques really work that well. So yeah, maybe with the longer retrieval windows now, you could push it a lot more and just dump the whole data set. But yeah, we didn't try anything like that.
optimize for, like, I wonder if there's like a set of like, perhaps examples you want to cover to optimize for a certain problem you'd like to prompt with a couple of different examples.
Sorry, what do you
Or
mean?
sorry, I mean, maybe like other optimal examples to include in your few shot prompt to, let's say, generalize, let's say, some desired like test sets up sample to optimize for it.
You mean based on the retrieval one or going back to the?
Maybe like perhaps this is like a hybrid of approaches where, let's say, for example, I want to design a better sorting algorithm. Then perhaps in terms of like problems that I'll put in my few shot example, I will give it perhaps more, let's say, sorting like problem.
Right, but that is what the retrieval is trying to do, right? So the hope here is exactly that we would find, yeah, we would find examples that look like the slow program that we're given, and then whatever optimizations were performed there will help improve performance of those models. Yeah. Yeah, so I think with really, really big retrieval windows, like 1 million contexts, you could just maybe dump the whole Pi data set in there and that would work. We haven't tried it. It might be something to try, but you know, retrieval does the trick as well. So the prompt for dynamic retrieval looks basically the same as the in-context learning prompt. So we just give it again, it's just 2 in-context learning examples. We give that to the prompt, and then we ask it to optimize the program. And in this case, we actually get a pretty sizable speed up. So our best model, now GPT-4 is performing best. Before we saw kind of, you know, surprisingly, maybe GPT 3.5 and GPT-4 were kind of performing similarly. And I think that's just because neither of them really knew what they were doing. But now that we have these really helpful in-context examples, GPT-4 is actually able to make really good use of them. And we get a 4x speed up for dynamic retrieval versus the best kind of black box techniques before was chain of thought, which only got 1.6x speed up. Yeah.
Sorry. How similar are the test cases to the things in the Pi data set? Like, you could imagine a world where this is like, you know, the sort of the answer's already there and it just picks it out. So how much is it actually generalizing versus just like the retrieval is solving the problem for you?
Yeah, that's a great question. So we were careful to split on the problem type. So CodeNet has problem types, and then each problem type has multiple submissions. So it's definitely, you know, we're talking about programs that are implementing different semantics compared to what's in the training set. But absolutely, they're the same kinds of, you know, it's not magic, right? So I'll talk a little bit more about some of the optimizations that it's able to do, and it is doing things that probably occurred in the examples that it's given. Yeah, I don't have a more careful analysis of that, but that's our intuition about what's going on. So yeah, this kind of shows that with when you make good use of the data through something like dynamic retrieval, you can, even in a black box way, do a pretty good job adapting models to solving new tasks, even when they seem to be very far outside what the models are initially capable of, which I think is pretty interesting. But, you know, we can still hope to do a lot better. So next I'm going to start talking about some of the fine-tuning approaches that we considered. So the first one that we considered was just a vanilla fine-tuning strategy. We have a supervised learning data set. Let's just use it to fine-tune our model. So basically what we did is we're still using a prompt. So we give it a prompt that basically looks like the initial instruct tuning prompt. But now we're actually training the model. So we're inserting the training examples into this prompt and using those to fine-tune the model. And then at inference time, we give it the same prompt and ask it to complete the sequence in order to get the optimized version of the code. So vanilla fine tuning. So here I'm just showing results for the code llama models. So I'll come back to GPT in a moment, but here for code llama, we found that we can get about a 2.7x speed up using vanilla fine tuning. Okay, so that's not bad. It's not as good as we might have hoped for, right? Because even with GPT-4 with dynamic retrieval, we were able to do much better than this. So just to compare, we're getting 2.7x versus 1.97x for code llama 13 billion, which again, it's okay, but I think we can still hope to do a lot better. So, well, let's step back for a moment and think about why vanilla fine tuning isn't doing that well. And the basic intuition is that if we're thinking about what the Pi data set contains, how we constructed it, we basically threw in every slow fast pair that achieved at least a speed up of 1.1x, right? So we have all this data, but to the model doesn't know that, the first pair that has a speed up of 1.1x is different than the second pair that has a speed up of 4.0x, right? But in practice, we know that the second speed up is much faster, and that's the really, if we're trying to predict the speed up in the future, that's really the one we want. But the model doesn't have access to that information because we haven't given it to the model. So when we train it, it's just going to interpolate between these two. Right. And kind of the underlying problem is if you're thinking, I said this is really a reinforcement learning problem at heart. And what we've really done is we've used imitation learning as a technique to reduce a reinforcement learning problem to a supervised learning problem. But when you do imitation learning, one of the things that's really important is you really want to make sure that you're training on the best demonstration. So all of your training data should be as good as possible, or you're going to kind of you're going to confuse your policy. And that's exactly the same thing that's happening here. So a really kind of straightforward idea to fix this is to try and only train on larger speedups, right? So let's be more stringent about what actually goes into our Pi data set. So we did that. We restricted to just about 4,000 of the fastest speedups distributed across different problem instances in our training set. And this actually does quite a bit better. So now we have another increment on top. So we've gone from 2.7x to 3.4x roughly. One thing I want to mention, so here I am showing results for GPT 3.5. We just didn't have the money to train GPT 3.5 on the whole data set. So that's why we didn't have results earlier. But we were able to fine tune it on this more limited set, and it actually does really well. So now that's going to be one of the best performances that we get is about 6.74x, which is fine tuning GPT 3.5 on just the high quality data. Yeah.
Is there a reason we're focusing on best of 8 instead of best of 1?
I mean, the best of 1 results kind of mirror the best of 8, but in this case, yeah, there's no reason not to just run the model 8 times and choose the best one, right, if we're doing program optimization. And really, one thing we're exploring now is running it for even more time. We used 8 because of just computational reasons. But really, you want to be scaling that a little bit more to get the best speedups. Yeah.
So how large is the data set that you're factoring
on? So it's about 77,000 pairs total. So yeah, cutting it down to 4,000 throws away about 95%. So it's a pretty big, yeah, I have the exact number here. Let me just bring it up. Yeah, so yeah, 78,000 pairs spread across about 1,500 unique problem IDs. Let me find where I was at. Yeah, was there another question? Yeah. I actually don't know, but it's not cheap. It's not that expensive, but it's not. I think if we had more time also, there was also a deadline crunch that restricted the results somewhat. Yeah, this is both. Yeah, well, we don't actually know what GPT 3.5 fine-tuning means, so it's doing something. And yeah, it is probably doing some kind of fast adaptation. I imagine, but I'm not sure. Yeah. Yeah. That's a good question. Wait, for 95 or wait, which number are you? Yeah, 59. So I mean, this is sampling with temperature, right? So I mean, actually, no, that's the Vesta one is not sampling with temperature. So I'm not entirely sure what's going on there, but it's not, the speed up is still better. So because we're training it, we're not training it to output the right program. We're training it to get the best possible speed up. So there is a trade-off there. We didn't explore it in that much detail, but it seems like if your correctness rate is too high, sometimes you actually get worse performance. And I think that's what's happening here. So it would rather risk being wrong sometimes to get faster speed ups. Yeah.
Yeah, that was my thought. That is, you have to be willing to make more radical changes to the code if
Right.
you want to get a big speed up, but it's more likely to be wrong as well.
Yeah.
Let's have a, maybe I'll ask this question later, but just to find it as well. Like, I think it's also curious to think about with respect to like collecting new kinds of data sets, like maybe this exception pirate, like at least for like code, like it seems like in some sense it's nice you can always like verify if the program ran correctly, compiled correctly, but like there are sort of like other aspects to it, like does it look nice? Like, does it like, whatever, like, or is it actually correct in some sense? So like, is there some notion of like correlation or code?
Yeah, I'll show some examples later. We don't get anything that crazy, which I think is actually one of the benefits of using LLMs. If you use traditional program synthesis, you can get pretty weird stuff. But LLMs are actually pretty regularized to writing human-like code, which I think is one of the big benefits of them, the kind of underappreciated benefits of LLMs. Any other questions? Okay, so this looks good, but we can still hope to do better. And the reason is that, it's great that we're getting these good results from training on the high quality data, but we have thrown away like 95% of our data, right? Which is not great. In a world where more data should always be better, this kind of feels like the wrong message. And it turns out that, again, coming back to this idea of imitation learning, there's something smarter we can do with the data to avoid throwing out so much of it. And we're really inspired by this idea of goal-conditioned imitation learning. So in goal-conditioned imitation learning, you use all your data, but you tell it what the goal that demonstration is trying to achieve looks like. So in our setting, that's going to be what we call performance condition generation. And the idea is instead of throwing the data away, let's tell the model what the speed up was for each element in our training set. And to do this, we had a really simple heuristic, which is we took our speed ups, we binned them into 10 bins, 10 discrete bins, and we just labeled each bin with a number between 1 and 10, with 1 corresponding to the slowest speed up, about 1.1, and 10 being the fastest speed up. And then when we train, we give the model information about which bin that example lies in. And then when we do inference, we basically just ask the model for the fastest possible speed up. So just to kind of illustrate this, so this is what our training data now looks like. So we have X's are not just the slow program, but also augmented with the speed up that was actually achieved. We get that just by measuring performance and putting it in the right bin. And then the Y, the kind of label, is the optimized program for that example. So now we're using all of our data. So we're not throwing anything away, but we still get to kind of exploit the fact that some programs or the model is still aware of the fact that some of these speedups are better than others. And now when we go into inference, so now we have a new program, we want to optimize it. We just tell the model, we really, really want the fastest possible program. And that's corresponding to the bin 10. So at inference time, we always use a speed up of 10 here. If you want a slower program, you could probably get that out too. But in our experiments, that's not what we were looking for. So again, so these are the prompts we use. It basically mirrors what I said above. So we give it the slow program and the fast program here. But we also give it a tag that indicates the bin. I think this is a bug. This should be the fast program here. Sorry, a typo. And then here we're basically showing the, we're basically asking for the fastest possible program when we're doing inference. And now, so again, we couldn't do this with GPT-5, but we were able to fine-tune code llama 13 billion. And as you can see, this actually led to a really significant speed up. So we went from 3.43x to 5.65x improvement in performance, which is, I think that's starting to get at where 3.5 is with just the high quality data. I do think if we could go back and we could actually train GPT 3.5 on with performance condition generation, I believe we would get even bigger speed ups, though, yeah, that's something that we haven't had the chance to do yet. So there's one more alternative solution that I wanted to mention. So for GPT 3.5, because of the training costs, we weren't able to use this strategy. So instead, we tried to just generate a little bit more high quality data and see if that could improve performance instead. So the idea is we just asked GPT-4 to generate a bunch of new programs. Then we asked it to optimize these programs. And then we retained all pairs that had a 5x speed up, which resulted in about 1,500 new pairs. So remember, we had 4,000 high quality pairs, and now we have 5,500 high quality pairs. Here's the prompt that we used to generate the synthetic data. But we did see a small speed up. This does suggest, I think it's not as big as we had hoped, because we thought, we have 1,500 more programs, that should help a lot. So I think it does suggest some of the limitations of synthetic data, but nevertheless, we do get a bit of a boost by kind of extending its, augmenting the training data set with synthetic data here. All right, so those are kind of, this really shows that, this performance condition generation, optimization idea, performance condition fine-tuning idea, if you can afford to do it, it's a really good strategy. Otherwise, fine-tuning on high-quality data gets you most of the way there. So one more thing I wanted to do is just show the comparison to human performance, just to kind of get a sense of what these numbers mean. So there are two kind of comparisons that I want to make here. The first one I think is really the more important one. That's the comparison and improvement for a human, the same human on the sequence of submissions that they make. So you have one person, they submitted 3 or 4 different copies of the to try and solve a single problem. They usually get a speed up of about 3.65x from start to finish. So this is why I said if you're looking at something like 1.5x, that's really leaving a lot on the table because your average human programmer can do much better than that. But if we're starting to look at some of these fine-tuning speed, so even the GPT-4 dynamic retrieval can exceed that. So that got 3.95. But then really when we're doing fine-tuning, that's where we really get much better performance than the average human. So we get 5.65 or 6.86, depending on whether you're using an open or a closed model. We also looked at the fastest programs across all humans. And here we were also able to beat that. So if you look at basically what we did is say, if you use just you always just use the fastest program generated from the human versus the fastest program generated by each of the separate models. The fastest human gets you about 8.9, whereas GPT 3.5 was able to get about 9.5. So we get a bit of a speed up even over the fastest human. Yeah.
A question from Discord. Are any of these fine-tuned models publicly available for use?
I don't know if they are now, but they will be. So yeah, we are working on releasing everything at some point. Yeah, so that shows that, at least in some ways, we do actually exceed human performance. So finally, this is just this kind of side note. We did also try low rank adapters, or LoRa, which many of you might be familiar with. We actually found that they worked pretty badly for fine tuning. Even on the high quality data, we were not able to get a very good performance. We were pretty surprised by this, but anecdotally, we've heard that from others that this is actually, if you have something that's quite far out of the training of kind of what the models kind of know very well, then LoRa actually doesn't work very well. So there is still a lot of space to kind of develop better low rank adapters. This is one of the reasons we were kind of limited to 13B, because we couldn't really fine tune 34B or 70B because we didn't have the kind of memory to do that. All right, so next, I want to kind of talk about an analysis of some of the improvements that we found. So we went through about 100 of the optimizations using our best model, and we looked at the kind of improvement that we saw. So first, about 34% of them were actually kind of fairly complicated algorithmic changes. So things like even we saw changing recursive methods to dynamic programming. About 26% was changing cin and cout to scanf and printf, which I didn't know this would make this big of a difference, but apparently it does. There were also some data structure changes, things like switching from vectors to arrays. And finally, there were some other miscellaneous changes. We just dumped everything else into that bin. But yeah, maybe a little bit more useful, just kind of going through some actual examples that I think nicely highlight the kinds of things we can do. So this is a pretty simple example where we're given a list of integers and we want to find the range of that list. So the naive solution, this was probably an early draft, but the naive solution is to just sort the list and then compute the range between the first and last element. That's of course not a really, that's going to be an n log n solution because sorting is n log n. You can do it in linear time if you just kind of do a single scan and compute the min and max. So that was a nice optimization. Here's another one where this was a modular arithmetic example where you were supposed to compute some modulus. And basically what happened here is in the kind of input example, in the input program, they were computing the modulus using a for loop, which is really slow. And if you just use the modulus operation, that's much faster. So that's, again, a kind of pretty low-hanging fruit kind of optimization that the model was able to find. The next one I think is actually a little bit more interesting. So here we had a loop that had an if statement conditional, checking, some specific condition, whether some specific condition was happening, and then it's printing, a space just at that one point. And the optimized code actually split it into two loops, so you don't have to keep doing this if statement check on every step, which I think it's a pretty somewhat non-trivial optimization, right? And it turns out that this actually runs a bit faster than having to do that if statement check on every single step. So yeah, just to kind of summarize, so we, with just a little bit of adaptation, we can actually make these foundation models, turn them into pretty effective program optimizers. But you do have to be careful how you do that adaptation. So we found that dynamic retrieval, and if you're doing black box or performance condition fine tuning, if you're kind of doing white box, these are the best, most effective strategies. But I think more broadly, I think there's just a lot of space to explore in how you actually adapt these models beyond the kind of really obvious ones that have been proposed in the literature. There are a couple of caveats I should mention. So there is the potential for data leakage because CodeNet is publicly available. The Pi data set, of course, is not, but I think this doesn't seem like much of a problem because if there is data leakage, it's not really teaching the models how to do program optimization. They're still not able to solve the task without some kind of fine tuning. Also, this next one is we are relying on test cases to evaluate correctness. Which is, so we don't have a guarantee, but we did look and our test suite seemed to be pretty effective. There were a couple of examples where there was some semantic differences, but for the most part, the programs were identical in the batch that we looked at. All right, so next I want to talk about a different project, also trying to look at adapting language models, but for a very different kind of task. So I think a lot of the flavors of the strategies that we looked at here are similar, but this is going to be applied to reward design. So just to kind of give a background on the reward design problem, so there's been a lot of kind of work in deep reinforcement learning over the last few years, and we've kind of been able to get really, really effective robots. So things like playing ping pong, manipulating objects like a cube, or walking on kind of very complex terrain. These are all really challenging control problems that reinforcement learning has really enabled us to solve to a large degree. But if you kind of look under the hood, there's a big challenge behind all of these, which is called the reward design problem. So we're assuming that there is a well-specified task, like get to the goal or win the game of ping pong, but this isn't the reward signal that people actually train models on. When you actually train the model, you're training it on a shaped reward that's designed to kind of guide the model to the task that you actually want to solve. And these rewards tend to be really, really complicated. So here are just a couple of examples from these papers of the rewards that they use. And they tend to require a lot of iteration to actually get right. And a very natural question is, so reward functions are just code. Can we use these models to solve the reward design problem? Yeah, I forgot to mention, so this is work that was led by my student, Jason Ma, and done in collaboration with NVIDIA. In this case, it turns out that instruct prompting is actually a pretty good starting point. So there was some kind of very recent work showing that if you just take the task description along with the environment code and you feed it to GPT-4, you can actually get pretty good reward functions out with very little kind of feedback. There are some limitations, so they do have to do task-specific prompt engineering for this, but it's actually pretty cool that this works. But it's actually also pretty surprising, because if you stop and think about it, we haven't told the LLM anything about, or we've told it very little about the environment. So we do dump the environment's code into the prompt. So it does get the code implementing the environment. But there's evidence LLMs don't really know how to execute code, so it's not like they can run the code and see what it does, right? If you're writing a reward function, you're going to write your reward function, run it, use it with reinforcement learning, see how well it works, and then use that as feedback to kind of improve your reward function. And in this space, it's really the same thing. We should be able to use the training runs in a simulator as feedback to try and improve the reward function. So I think this is a really natural idea. Basically, we're going to sample a bunch of different reward functions from GPT-4, just like I told you. And then we're going to run each reward function in the simulator. And then we're going to, we have basically some heuristics for identifying portions of the reward function that don't really contribute much or degenerate in some way. And then we'll tell GPT-4, look, this is some of the feedback that we got from the simulator. Can you use this to actually do a better job? So yeah, I think someone asked about using feedback. So in this case, we actually did find that the feedback was really effective. So now we have this loop. And I think the reason the feedback is effective is because we're giving it access to this simulator, which it really knows nothing about. So this is something that GPT-4 doesn't really know what the simulator is doing, right? So here, we're giving it really useful feedback in order to improve its reward design. And we found that it can actually do quite a lot of interesting edits based on this feedback. So here, it's just changing the hyperparameters. So that's a pretty straightforward one, but it can also introduce some pretty interesting constructs. So here, it's doing something weird with the reward where it's passing it through an exponential and then clamping it, which we don't really know why, but it actually worked really well. I mean, it can add entirely new terms to the reward function as well. So here, originally, the reward was just some reward for the rotation plus some reward for distance, but now it's adding a penalty on the angular velocity, which turns out to help. So that's those are some examples, but we ran this on a big benchmark of dexterous manipulation tasks. And we found that, I mean, basically the takeaway here is that with 5 rounds of feedback, we were able to actually exceed human performance. So we were able to do better than the original. So starting from scratch, we synthesized a reward function that was better than whatever the original environments had come in. So these environments all came with reward functions that humans had designed, and we were able to outperform them in terms of, we run the same RL algorithm and we get better performance. And we were also able to beat the kind of basic baseline that I mentioned where we don't do any feedback. So that's the green line here. Red is human performance and green is the kind of naive baseline. And one cool thing is we were also able to solve a pretty challenging control task in simulation. So here, this is supposed to simulate a pen spinning task. So we have the shadow hand that's spinning a pen. Some more work went into this than just the vanilla framework I mentioned, but we were able to design rewards that got this to work. So Yeah, I think again, so the takeaways, I think similar to last time, you have to be careful how you think about adapting your models to these new tasks. But by incorporating feedback, the right kind of feedback, we were able to get these foundation models to write highly effective reward functions. And also, I think more broadly, this kind of illustrates how we can use coding LLMs in order to solve challenging AI tasks. And finally, just for the last few minutes, I want to talk about one more project on conformal prediction for code generation. So this is just looping back to the second challenge I mentioned at the beginning about how do we deal with the fact that LLMs can write buggy or incorrect code. And really, this is a problem not just for coding LLMs. LLMs also hallucinate for things like question answering, summarization, and a lot of other tasks. So we really need better tools for dealing with these issues. So how can we improve the trustworthiness for LLMs in these kinds of contexts? So for the programming setting, a kind of ideal would be to use tools like program testing or program verification, because it does give much stronger guarantees about code correctness. But these techniques tend to be pretty hard to scale or generalize, right? Like if you're writing some code in the middle of a really complicated code base, you're using functions that are hard to specify. You might not have test cases and so on. So it can be really hard to incorporate these kinds of techniques into code generation, kind of code generation interfaces. So we've been doing a lot of work on a different strategy, which is to quantify the uncertainty of the model. So this gives a much weaker form of correctness. We're just trying our best to kind of capture when the model is uncertain, but it can be really effective at targeting user attention and fixing the kind of most uncertain parts of the code. So we're going to be, and I'll talk about this more later, but the main challenge is, so there's been a lot of work on uncertainty quantification for things like classification regression, but doing it for structured outputs such as code is a lot more challenging. So we're going to be building on the conformal prediction literature, which is a set of techniques from statistics for quantifying uncertainty of models. And the idea in conformal prediction is that you take a traditional pipeline. So here I'm going to illustrate this with ImageNet. So this is an ImageNet from the ImageNet data set. If you feed this to ResNet, it'll give you a label like toilet seat, which seems like a pretty reasonable prediction for this image. Right, but it turns out that if you look in the ground truth in ImageNet, the right label for this is actually plunger, which is also a plausible label, right? So this example kind of demonstrates that there is intrinsic uncertainty that is really hard to get rid of. So the idea in conformal prediction is to kind of handle this by, rather than just predicting a single label, we're going to predict a set of labels instead. So the alternative is to try to do predicted probabilities, but I find that, especially we'll see in structured prediction, I think having these prediction sets will be a lot more interpretable for end users than just giving them some confidence. But in particular, you can see that we do still include the top label of toilet seat here, but we also include the ground truth label of plunger, right? So this set kind of captures the underlying uncertainty in the model. And one nice thing about conformal prediction is it can actually give guarantees on this property. So we can guarantee that 99% of the time, for example, the prediction set contains the ground truth label. So just to kind of give a very high-level sketch of how conformal prediction works, the basic idea is that, so it's going to choose this parameter tau in a careful way. But then once it has tau, it's going to construct prediction sets by basically looking at the label probabilities and adding labels to the set until they add up to at least tau. So this threshold tau, you need to choose very careful if you want to get the coverage guarantee. But you can always make it really small or really large to get kind of everything. But you need to choose it carefully to kind of get the smallest possible prediction sets while still getting your coverage guarantee. But yeah, the basic idea is just this. We're going to keep growing our prediction sets until we hit a threshold tau. And so let's think about how we might do this for code generation. So the idea in the code generation setting is that we're going to take a true program. And so maybe we have a true program that we wanted to target, like the Fibonacci program. And then there's a generated program that and we want to kind of quantify uncertainty, right? So here, clearly, it's not getting everything right. So the 0 should be a 1 and the 3 should be a 2. And if we look at, you know, a natural prediction set for this program, it's going to be really large, right? Because it basically includes every possible thing that we could use to replace 0 or 1. And this is the challenge with structured generation. So if you have structured outputs, your naive prediction sets might contain thousands of programs. And basically, our idea for solving this is going to be to use compact representations of sets of programs. And basically, the idea is we'll implicitly represent prediction sets as a partial program. So let me just illustrate what that means in the context of this example. So here we have this really large prediction set. And what we're going to do is we're going to implicitly represent this prediction set with the following partial program. So it's partial because basically we've taken the 0 and the 3 and we've replaced them with these question marks, which are called holes. Okay, so now we have this partial program that implicitly represents the set of all programs that can be obtained by filling the holes in some way. And now we have a really interpretable representation of uncertainty. So yeah, in the interest of time, I'm not going to kind of say much about how we construct the prediction sets, but basically we're just going to prune nodes in our AST until the total probability mass that we've pruned exceeds tau. And that gets us the same kind of guarantee as what we got before. So in this example, if we delete 0 and we delete 3, it turns out that we satisfy the tau threshold. So we get a prediction set that actually covers the ground truth program. And here we can see a different example. This is for SQL. But we can, again, get a prediction set that kind of highlights the uncertain parts of the program. And we guarantee to the user, if you kind of just fix these parts of the code, then 99% of the time, you're going to be able to get a correct program out. So we did do so we had a kind of a special optimization strategy for actually computing these partial programs. And we showed that it kind of does much better than a naive greedy baseline. So we get much smaller prediction sets while getting the same level of coverage. So just to summarize, I think, you know, uncertainty is a really important way to improve trust in these systems. And for code generation, I think, you know, for each domain, you're going to have to think about how you want to represent uncertainty. And I think for code generation, partial programs might be a pretty good choice. And so, yeah, that's everything I had. And thanks for listening, and I'll be happy to take any questions. Yeah.
I would love to dig into this stuff in terms of the conformal prediction. So, I mean, this seems like a fairly general purpose set of techniques in terms of like being able to back out and say, I have this part of the program that captures most of the semantics that I want, while still, you know, being a little bit humble. So, for example, it seems, you know, it could probably be harder to do, for example, like program optimization with that because the AST is so similar other than these leaf nodes. That maybe you could like, you know, I guess find bugs more easily if there's like an off by 1 error in the code. It's easier to identify that. I guess I'm curious, how are you thinking about like the main applications of those sorts of techniques of partial programming? Is it mostly for theory and interest, or is it, you know, what would you do with it?
Yeah, I think code completion is what we had in mind when we started this work. Yeah, I do think for program optimization, it might not make as much sense because you might still want to highlight. I mean, if you have test cases, you should use those. This is for cases where you might not have tests, and I think doing program optimization in those settings is quite challenging. So yeah, we were thinking about code completion. So I could easily imagine something like Copilot could benefit from doing a better job showing users which parts of the code are uncertain, for example, or GPT-4. Yeah.
I have 2 questions. I guess the first, is there any thoughts around maybe balancing other objectives? Like one that comes to mind would be if you're working like a web interface, maybe having like attack services and security as an issue, and how that can kind of maybe fight or conflict with the like speed as an objective for code generation.
You mean if you want to do code completion in the program optimization, but you have like code that you're
around, you need to be secure or limit your attack services or something.
Yeah, that's a great question. It's not something that we've thought about very much. I mean, if you are using secure code, you could imagine using program analysis, for example, to check that certain constraints hold. But we are kind of leaving it up to the user to validate the code that comes out at the end, right? So if you do have checks that you can run on the code, then you can absolutely incorporate those into our pipeline just the way you do tests, and it would work the same. But if it's something that's kind of a little harder to formalize or check automatically, then it is ultimately up to the programmer to choose the one that kind of balances security and optimality.
And then in the like different speed ups that you had listed on that one slide with algorithmic, there was one that was kind of like it identified these algorithmic primitives and that was just using them in the right place to like create a speed up.
You mean this one here?
Yes.
Yeah.
Have there been cases where it has tried to apply like I guess these algorithmic changes in domains that haven't been used before, or is there any like novelty in those predictions, like in those generations, or is it just like kind of?
Yeah, that's a good, I mean, it's hard to be sure, right? Because these things are hard to check. So I can't really, I mean, we weren't able to really look into that. I would imagine most of what it's doing is taking things that had happened in the data set and applying them in slightly different or novel like it's not doing literally exactly the same thing because it is solving, we are looking at different programs for different tasks, right? But I don't think it's like inventing new optimization techniques here because in some sense, if it was, I think we would have seen better performance without the fine tuning, right? The fact that we need fine tuning means we needed to tell it what the optimization space is.
Yeah.
So my guess is that it's just taking things that it saw in the training data and adapting them to new contexts, but it's hard to be sure. Yeah, but that's a great question. And we don't really know how to probe these things. So if you have any ideas, we'd be happy to hear.
Do MapReduce or something.
Yeah. I'm guessing it's not doing that. So that, I mean, yeah, I kind of motivated, Alpha Dev is trying to do something that is a little bit more kind of new, though even there's, they're optimizing assembly. So I think, but yeah, I think you would need to do a lot more search if you wanted to do something like that. I think doing just a few shot like deep learning system isn't going to be capable of that I know of. Yeah. Question.
Yeah, any thoughts on combining some of those like reasoning, explanation, chain of thought type approaches with the fine tuning approaches, perhaps for more like interpretability? It seems like it would be hard to create a data set because then each slow fast pair would need to be associated with an explanation for.
Yeah, that's a great point. We actually did think about using GPT to generate the explanation and then having it do chain of thought on that. I think I don't know if we ever got around to trying that. I definitely think there could be some benefit from that, especially in terms of interpretability. Yeah, but there are just a lot of different combinations, so we had to kind of pick and choose which ones we focused on. But yeah, I do think there is a lot to try here, and that's certainly something that could help, even in terms of performance, but certainly in terms of interpretability. Yeah. Do you have yeah.
I have a question about potential hallucination associated with the conditioning of performance or performance condition. So I imagine most of the, like, say, 8, 9 speed improvements come from the slow program being really terrible. But if you are feeding it a okay program to improve upon, let's say score 5, and there's no pair of a 5 to 9 improvement in the actual data. So would it just generate a garbage?
I mean, there will be pairs of like, there should be pairs. I don't have the statistics on that, but I imagine there are pairs like that in the data set. Because if you're looking at, because we actually look over all pairs of improvements, right? So if you have something in the middle and then you get something at the end, I think then you would get some kind of pair that improves from a medium to a fast program. I mean, we do know that like we're basically outperforming even the best human to a little bit. So clearly we are eking out something more than just going from the slow to the fast, right? I mean, even replicating that, I think we would have been happy with, but there is something kind of more that's going on here than just kind of going from the slow programs to the fast ones at the end. Yeah, so like this number says that if you, basically the way to interpret this is if you start from a random program by an individual, we're going to end up with a faster program than that individual ever got to. Yeah.
Apart from like the robotics and simulation, do you think of any other use cases or domains that automatic reward function generation should be applied to?
Yeah, I think there are a lot more that we've actually been exploring recently. So we've also looked at walking, like we have a walking dog robot that we've been playing around with, and it works there as well. It's really the caveat is this is mostly focused on low-level control, not high-level planning, which I think is kind of a very different problem. But I think for a lot, like we've also, I don't know if we got it to work with drones, but that's something else we looked at. Any kind of lower level control, I think you could feasibly use this to do reward design. Yeah.
Just maybe like 2 questions. One at a higher level, I guess how bullish are you with respect to kind of like essentially like maybe some form of supervised fine tuning to solve, let's say, I don't know, optimizing code problems or in general sort of like writing this thing maybe like more alpha code. Yeah. Do you think like just with enough high quality data, we can capture these same kinds of like traces just by training the model to break the next step then?
Yeah, I mean, I think if you have good data, I don't see why not. I mean, at the end of the day, reinforcement, like AlphaDev is still using the same architecture of model. They're just using a different training strategy. So I don't, if you have good enough data, you should be able to get the same ultimate quality with much less compute, right? I think where you need reinforcement learning is where you want to kind of exceed the quality of the data that you have. That's really where if your data, so if you wanted have superhuman performance, then reinforcement learning is almost a must because you're not going to get the kind of performance you want from purely looking at human generated data. But I would argue that for a lot of tasks, we're not looking for superhuman performance. We'd be perfectly happy with human level performance. And for that kind of stuff, there's no reason not to use the data that you have available.
All right. With that, thanks so much.
Thank you.